Okay, are you seeing it, Jiwon?
Yes, everything is good.
Okay, great. Yeah. Hi, everyone, and thanks for the invitation to speak today. I want to tell you a little bit about our efforts to make new adsorbents for carbon dioxide that operate by a different mechanism from traditional adsorbents via a selective cooperative adsorption and desorption mechanism. And the materials that we work on are metal organic frameworks. So metal organic frameworks to us are essentially designer porous materials like zeolites, but they're constructed of metal ions with organic molecules that stitch them together into a porous three-dimensional architecture. And what's special about them is that they're extremely chemically tunable. So we can control pore size, shape, and surface functionality. And it's that tunability combined with record high surface areas that make them very powerful for things like high density gas storage and high capacity molecular separations. And so today will be specifically about trying to make materials of this type with a strong affinity for CO2, but exhibiting this property that hadn't been realized previously in such porous materials of selective cooperative adsorption. So in terms of use, the simplest way for using one of these materials would be to load a column with the solid adsorbent, bring the mixture, say CO2 containing flue gas in at one end, and as the gas runs through the material, it should selectively adsorb carbon dioxide and let all of the other molecules out the outlet at the other end. As you do this, eventually you'll saturate the adsorbent with CO2. And at that point, you'll either raise the temperature or lower the pressure and release CO2 in pure form for utilization or sequestration. And then you start again. And so these materials need to be able to sustain millions of cycles, ideally, for adsorption and desorption of the CO2. And essentially, any adsorbent that you would normally put into such a process, such a column, has a Langmuir type response to the gas molecules. So this is under equilibrium conditions, and this is just a plot of gas uptake versus the pressure of the gas. And for Langmuir adsorption, non-cooperative adsorption, you have this steep rise at low pressures, and then it turns over as you saturate and coat the surface of your adsorbent. And in such a scenario, once you've loaded at your adsorption conditions, the pressure of CO2, the partial pressure of CO2, and whatever temperature you're removing it at, to desorb pure CO2, then you either need to go to very deep vacuum or drive to very high temperatures to have any reasonable separation capacity. And if you were just to try and reimagine what these isotherms should look like for a very efficient CO2 separation, then you probably wouldn't come up with Langmuir isotherms. Instead, you might come up with something that looks like a step. And so step-shaped adsorption isotherms can arise for cooperative adsorption processes. And what it means is that in such a case, you go to a sudden condition where you go from no loading of CO2 to hitting a temperature and pressure where all of a sudden it's spontaneous for CO2 to load into the material. And at that point, you can go from no loading to filling up your material with carbon dioxide. So there's a switch-like behavior. And that means that you could do then a very small pressure drop to release the CO2, or if you're doing a temperature swing, a small temperature increase. And so this would be a big advantage, but it had never been realized in a dense way in a porous material. And there are a number of ways you can create stepped adsorption isotherms for adsorbents, but the way you'd like to do it is with selective binding, akin to how hemoglobin captures oxygen. So most chemists are familiar with hemoglobin, but here you've got 4 iron heme sites, and when oxygen selectively binds at one of those iron sites, it triggers a rearrangement of the protein backbone and opens up access to the other 3 iron hemes for oxygen binding. And so hemoglobin essentially has a breathing sort of mechanism where it will simultaneously bind or release 4 oxygen molecules at once. And so the adsorption isotherm that you get is shown at the right. You see a step instead of that Langmuir shape. And this allows hemoglobin to either fully unload or fully load with oxygen in a very narrow concentration window. And so nobody had seen this sort of thing in a dense form in a porous material until we serendipitously discovered it, not for oxygen, but for CO2. And the MOF that we found this in is one that is built on magnesium 2+ cations stitched together by this organic linker shown at the left. This linker is deprotonated 4 times, and that 4- anion stitches the magnesium ions together into a honeycomb type structure. And these channels running through the honeycomb are about 18 angstroms across. And if you were a CO2 molecule and you approached a crystal of this MOF and you entered one of the channels, then you'd have a view like this. So this is looking down one of those channels. And the green spheres that you're seeing are the magnesium cations. And so you can see at the corners of the hexagonal channel, you have rows of magnesium 2 centers. And those magnesium centers are spaced about 6.5 angstroms apart. And to capture CO2, what we did is we added a diamine, one diamine like ethylene diamine, to every magnesium center shown in green. And that creates rows of magnesium diamine running along the corners of each channel. And it turns out that the spacing for those chains are just right to polymerize CO2 into ammonium carbamate, one-dimensional solid. And so to do that, our next step is to graft a diamine. This is dimethylethylene diamine. One goes to each magnesium site in the structure. And nicely, MOFs are crystalline materials, and so we can actually get crystal structures of what the material looks like before and after CO2 adsorbs. So here you're seeing a slice along one of the channels. And so instead of green, they're shown in pale blue here. But the metal centers initially each have a diamine attached. And when CO2 adsorbs, it's going to insert into a metal-amine bond to form a metal-bound carbamate. And simultaneously, you'll transfer a proton from the backside of the amine you're inserting into to a dangling amine on the next site down the channel. That ammonium cation is attracted to the carbamate anion, and you can think of that as tugging on or activating this next metal-amine bond for CO2 insertion. So the product you get is a one-dimensional ammonium carbamate chain, one of those running along each corner of every hexagonal channel in the material. And so here we got very lucky. The ethylene diamine is just the right length to bridge CO2 adsorption sites and create a cooperative polymerization adsorption process. And so this material indeed shows very nice step-shaped adsorption isotherms. And this is the first observation of such steps and cooperative adsorption for CO2 under such conditions that might be relevant, say, to capture from a flue gas or even from air directly. And you can also see here, these are adsorption isotherms collected between 25 and 75 degrees C. As we increase the temperature, those adsorption steps move rapidly to higher and higher pressure. Also, the capacities here are generally 3 to 4 millimoles per gram, meaning up above 15 weight% CO2 uptake. So these are high capacity, and you can swing the full capacity of the material because of the step-shaped adsorption isotherms. And so this is the main advantage of these cooperative adsorbents compared to amine solutions or other amine adsorbents. You can do a small temperature change, say 50 degrees C, and have a large amount of CO2 removed in each swing. So lower temperature, of course, means lower energy consumption and lower cost. So we learned how to manipulate the CO2 adsorption properties of these materials. And there are a number of knobs you can turn to change what conditions, what pressure and temperature will trigger the sudden onset of CO2 being taken up. And so in general, the easiest way to adjust that step position is to change the structure of the diamine. So you can imagine, since we're inserting CO2 into a metal amine bond here, the nature of that bound amine will affect the thermodynamics of that reaction with CO2. The spacer between the two nitrogens for a diamine will control the structure of the ammonium carbamate chains that you're forming, and that will affect thermodynamics. And then also the substituents on this ammonium forming nitrogen will also change the strength of the ammonium carbamate interaction and affect thermodynamics. So all of these are knobs we can turn to adjust and change the CO2 response and try to customize it for various different incoming streams containing carbon dioxide. And so here is a plot just showing the thermodynamics and how in this inexpensive magnesium-based MOF, just changing the appended diamine will vary the delta H and delta S of CO2 adsorption. And so there's a dozen or so different diamines appended to that same base MOF. And you can see, you can change delta H from anywhere from minus 40 kilojoules per mole to out past minus 100 kilojoules per mole. And as you do that, as you increase the enthalpic driving force for polymerization, at the same time, you're making more and more tightly wound chains, and you're paying a larger and larger entropic penalty. And so our adsorbents tend to fall along this master line, the gray line. And so we've studied now many different diamines, more than 80 different diamines in this material. And at 40 degrees C, we can adjust the step anywhere from 2 parts per million, where you're capturing very deeply from air, to past 2 bar, which might be useful for a high pressure gas mixture doing the CO2 separation. So of course, there are many, many places we'd like to efficiently remove CO2 from a mixture, and we need to be doing a lot more of this. But by changing the diamine, we can try to optimize for a separation process targeting these various CO2 containing mixtures. So one thing that we've had in terms of projects for a long time is we've worked with ExxonMobil on trying to create a MOF that could do cooperative CO2 capture at high temperature conditions from a natural gas fired power plant flue gas. And so that's a concentration of around 4% CO2. But they also had a process where they wanted to use these at high temperatures, where you could capture at high temperatures and minimize this water coadsorption from the flue gas. And so one issue is if you're working at very extreme conditions, very high temperatures, then from some of these adsorbents, you might start to volatilize the diamines. And you would gradually lose capacity as you would adsorb and desorb CO2 at these very high temperatures. And so from looking at crystal structures, we had the idea that we might be able to connect a pair of diamines in the adsorbent and create a tetraamine that would still allow this cooperative chain forming mechanism. And so here's just an example of such a tetraamine that we tried. And excitingly, these tetraamines, when you load them into the MOF, they actually organize themselves. And so you can get crystal structures showing how they're organized. And so here's on the right is a top view. You can see each tetraamine is bound to 2 metals instead of just 1. And there's even some hydrogen bonding between tetraamines. And so these materials can be really effective. In fact, you can capture from an NGCC flue gas stream at 100 degrees C and have essentially negligible water coadsorption. And then desorb under various conditions, including going to say 180 degrees. This is showing the last 200 and 1,000 desorption cycles, showing that we're not losing any capacity for CO2. When we saw that these could operate under extreme conditions, we thought perhaps we could regenerate with steam, do direct steam stripping of the CO2. And so those are very harsh conditions for most adsorbents. They're not going to tolerate it. But these are very stable. These tetraamine appended materials are very stable. And in fact, you can regenerate using direct steam stripping. And this is showing just isothermal CO2 adsorption and desorption. These are infrared spectra, and the central band is the carbamate CN stretch, and showing that this chain forming mechanism is operational. And so you could actually use low heat steam, low quality steam for electricity production, even as low as 110 degrees and lower to remove the CO2 from such an adsorbent. And that can cycle. It's challenging to do these cycles, but we don't see loss of capacity here as we cycle CO2 and strip it out with direct steam contact. So here's just a video showing you how this works. So here we're focusing in on one channel of the MOF with the tetraamines loaded, and we'll rotate 90 degrees now. And looking down on the MOF, the rows of tetraamines. And it turns out there's actually different thermodynamics slightly for the first chain at one end that forms and the second that forms at the other end. So you see a double step instead of a single step. Once you've loaded with CO2, you can apply steam, release the CO2, and then you start again. So I want to just finish by saying a couple of words about air. So we've been looking at these types of materials for capture of CO2 directly from air. This, of course, is the most difficult separation that we need to do in terms of removing CO2 from all kinds of sources. Because of this very dilute nature of CO2 in air, there's already a much higher minimum work that we'll have to do the separation. And so unmixing this very dilute CO2 from air comes with a big entropy penalty. And so this is a much bigger challenge, but we've seen that we can see very good performance from materials of this type. This is showing isobars under 400 ppm of CO2, showing you see it again, the step is indicating that cooperative CO2 process. The blue data is upon cooling. So at low temperatures, you're having a high capacity for CO2 removal from air. And then when you warm, you can see even by 90 degrees at this, with a vacuum, you've pulled off the CO2. These can cycle at high capacity under various conditions that we're now testing. So those materials were interesting, and actually the PhD student who initially discovered the cooperative CO2 adsorbents was Tom McDonald, and together we started a company to try and scale up and test these materials in a practical separation. So this company is Mosaic Materials. Actually, Ju Wung was as a postdoc, started out as working part-time in starting this company. But the real technology that was developed there was, how do you make these materials inexpensively at large scale? And how do you make them in structured forms that are robust and don't pulverize under working conditions? And so at the right, you can see MOF pellets being bashed around, testing and showing that they're not coming apart. And so we got to a point where we thought this technology was ready to be deployed. And so last April, Mosaic Materials was acquired by Baker Hughes. So Baker Hughes is an engineering company. It used to be a big part of GE, but they manufacture, for example, turbines that are used in power plants. They have 55,000 turbines, giant turbines deployed worldwide. And we're hoping that these materials might be integrated and used for capture from those turbines. But the first technologies that are being deployed working with Baker Hughes are for direct air capture using these materials. So I want to finish and thank some really fantastic students, postdocs, collaborators, these sources of funding, and I'm happy to answer questions.
Thank you very much, Jeff, for the amazing talk. I think